Okay, it's 5:30, so let's go ahead and get started today. Good evening, everybody. How's everybody doing today? Good, good. Yeah, week 9. Definitely getting there. So we're, just to kind of continue off where we've been going. We're starting kind of a new thing with this finite elements. So, what we're going to do today is, we're going to build off what we did on Monday, and we're going to do an example of, we're going to start off with an example to basically show you how do you actually solve these kind of 1D boundary value problems with a finite element formulation. So, you'll see some familiar stuff. So, you'll see some element stiffness matrices. You'll see a global system. You'll see, a linear solve. But the way that we approach it is going to be really different. Okay. Okay. So before we get started with that, are there any questions? Okay. Oh, so a new homework was posted too. So I think I posted that yesterday. I think it should be due next Friday. I think that's the due date for that, if I'm not mistaken. Let me double check. Yeah, it's gonna be due next Friday, so October 30th. That's when the homework's due. Okay, and so it'll cover basically everything we did last week, and then up to everything that we're gonna do today. For the homework. So after today, you should have everything that you need for the homework. Okay, so let's get started. All right, so we went through a lot of math last time, so I kind of just want to before we start, I kind of want to summarize our process. Okay, and so this whole week is basically we're dedicated to finding a finite element solution to a boundary value problem. And so remember, a boundary value problem is defined as a governing differential equation and a set of boundary conditions. Okay, and so we've gone over basically 2 examples of boundary value problems that you'll see probably in practice. And so we've gone over 1D elasticity, so that's going to be our structural mechanics problems. And so we're solving those problems basically for the displacements at all the nodes. And then the other type of problem that we've been looking at is heat conduction. And so for those problems, we're solving for the temperature distribution within a 1D rod. Okay. Mathematically, they're exactly the same problem. So it's still they're both going to be a second order differential equation, that involves some scaling parameters. So the 1D elasticity has your Young's modulus, and the heat transfer have your thermal conductivity. And then to that, we're going to add our forcing function. So both of them mathematically the same, but they model kind of different stuff. Okay? And so the process of taking a boundary value problem and finding a finite element solution can be summarized by the following. Okay? And so the first step is to discretize our domain into finite elements. Okay. And so, before, in all the problems that we've been doing before the midterm, this discretization was provided for you. And actually, all we did was basically just define each structural member to be one element. Okay? But in these problems, it's up to you how you discretize the problem. Well, it's not really up to you because, just because, I want everyone to be able to check their answers in the same way, I'm going to give you the discretization, but in theory, you can discretize however you want. Okay? And so, for these 1D problems, we have like a 1D domain like this, right? And so let's say that we have, a bar of length L, okay? And then to discretize it, we can basically break this up into lots of smaller bars. Okay? Okay. And so that's a discretization, right? And so one thing that we'll see in our first example is that you don't have to pick a discretization like this, okay? And so in this discretization, you can see that all of our elements are roughly the same size, but you can easily have a discretization that looks like this, okay? And so you can have elements of actually different sizes, right? And that's okay. And actually, there might be some situations where this is actually more valuable, okay? Because you might run into situations where you're solving for the finite element solution, and you're more interested in what's happening, say, like on this side of the bar. Okay? And so if you're mostly interested in that side of the bar, you can add more elements and more nodes over there, okay? But if you're not really interested in what's happening over here, there's no point in putting a bunch of elements there and doing all that work for stuff that you don't really care about, okay? And so we kind of saw this a little bit in our very first ANSYS activity where we applied refinement around the hole, right? So if you remember that from that first activity, we refined the elements around that hole such that we got a finer mesh resolution around there, okay? And so you can do the same thing here. So, depending on where you want kind of the most accuracy in your simulation, you can choose to discretize more in that area or not, okay? Okay. And so the second thing that we did, and this was kind of what we did for most of last time, was we had to assume, a functional form, okay? Okay. Because we're not going to be solving these equations directly, we need to know kind of what we need to know what form of the solution we're going to be looking for in the end, or basically what is our solution going to look like, right? And if you remember, this was mostly based off the form of the weak form, right? And so because our weak form only has first order derivatives, the simplest function that we can use are linear functions. And so linear functions are actually really nice because they're simple and they don't have that many constants, and we can solve for it pretty easily. Okay. All right. Once we assumed a functional form, we can form our element stiffness matrix. Okay. And last time we derived the expression for the element stiffness matrix based off our linear shape functions last time. And so you can basically just apply that formula. And then one thing that's also new in this case is that we're also going to get an element forcing vector. Okay. And so when we go to assemble these problems, we have to not only add together our element stiffness matrix, but also our element forcing vector as well. Okay. So I'll show you basically how to do that once we get to the problem. Okay. And then from here, once we have our element stiffness matrices, the process is exactly the same as what we did in the first half of the class. So from here, it's all familiar stuff, so we can assemble. Okay. We can apply boundary conditions, and we can solve. Okay. All right. But this is kind of the general framework that you follow. So if you come across a problem where it asks you to solve for a 1D finite element solution, you basically just follow this recipe. So the only one that you probably don't do explicitly is step 2, because step 2 is kind of baked into the expression for the element stiffness matrix. Okay? So the only time where you would do step 2 is if there were a reason to use, like, maybe a quadratic shape function or a cubic shape function. Okay? But for most of the problems I want to make you do by hand, I'm going to let you use linear shape functions, just because, once you get past linear, it starts to become pretty nasty. So, think of like a frame problem with like 6 different elements for 5 nodes. So, it's not a fun thing to do. I mean, you guys would definitely be able to do it, but it's not the best way to spend the next 2 hours of your life. Okay, any questions on this before we jump into an example? I just realized I drew Baymax here unintentionally. Okay, so let's jump into an example. Okay, and so in this example, let's consider the following bar. Okay, and so this is going to be a structural mechanics problem. So on the left-hand side here, we have a fixed support. And so on the right-hand side, we're going to have a compressive stress. Okay. And so this is going to have a value of -5 pascals. Okay. And then on the interior of the bar, we're also going to have a body force. Okay. And so that's going to be given by B of x is equal to 2 newtons per meter. So let's define the length. And so the length here is going to be 2 meters. Okay. And then what else do we have? So we have a Young's modulus. And so our Young's modulus is going to be 5,000 pascals. Okay. And our area is actually going to be changing. So, as we move along the bar, the area is actually going to be increasing. So we're going to have 1 plus x squared over 400. Okay. And so we're going to need to take this this varying area into account. Okay. Okay. And so for this problem, we want to find a finite element solution. Okay. And we're going to do so on the following grid. Okay. And so I'm going to do just 2 elements. Okay. And so I'm going to number these nodes 1, 2, and 3. Okay. And so at these nodes, we're going to have the solutions U1, U2, and U3. Okay. We'll call this element A, and we'll call this element B. Okay. We'll say that the length between node number 1 and node number 2 was going to be 5 meters. Okay. Oh, sorry, this length is 20 meters, not 2. Okay. And the length between nodes 2 and nodes 3 is going to be 15 meters. Okay. All right. And then for this finite element solution, we're going to use linear shape functions. Okay. Question? So the question is the U2 point just arbitrary? So remember what I said before. So the discretization, or where you put the nodes and the elements, it is somewhat arbitrary. So you can choose to discretize this however you want. For this problem, and for the problems that I'm going to ask you to do, I'm going to tell you the discretization. But a lot of times, you can choose this however you want. Okay. For most of the time, the way that you choose the discretization is based on how much accuracy that you want. And so the more elements that you put in, the more accurate your solution is going to be, because that's going to make your linear system bigger, and it's going to allow you to solve for more nodal values. So, so there's always going to be a balance of kind of cost versus accuracy. Okay. So the next question is, how do I know how to use linear shape functions? So, so for all the problems I'm going to make you do, I'm going to make you just do linear shape functions, because once you do quadratic, the element stiffness matrix just kind of gets a little bit crazy. But in reality, how you choose between linear and quadratic shape functions kind of depends on the problem that you want to solve. So we'll talk more about this after the second midterm, because after the second midterm, we'll be talking a lot of practical considerations for if you're going to use ANSYS out in the real world or some other software. And so how do you choose between linear and quadratic? So there's certain situations and there's certain criteria that you can use to choose between linear and quadratic. But just to give you kind of a quick nutshell, so linear shape functions, obviously are going to be simpler and cheaper, but they're not going to be as accurate for certain things. Whereas quadratic shape functions, they're a little bit, they cost a little bit more in terms of time and in terms of memory, but they give you kind of more bang for your buck. So, and that's particularly important actually for structural mechanics. So in structures, you're interested a lot in the structural stresses, how much stress is this structural member going. And quadratic shape functions do a much better job of estimating stresses than linear shape functions do. So, but on the flip side, if you're solving a heat transfer problem, for heat transfer, kind of the equivalent quantity for stress is heat flux. And so a lot of times heat flux isn't as important of a statistic that you want to look for. So in heat transfer problems, it's often better to use linear shape functions, just because it's going to be a lot cheaper than quadratic. Yeah. But we'll talk a lot more about that after the next midterm. Yeah. Okay. So that's the problem. And so now that we have the discretization, and now that we've chosen the shape functions, the next step is going to be to form our element stiffness matrices. Okay. And in this case, we're going to have two of them because we're going to have an element stiffness matrix for element A and an element stiffness matrix for element B. Okay. And I'm going to do that on the next page. Okay. Before I do that, are there any questions on this before we start working this out? All right, so the question is, can we place U2 in the middle? So absolutely. So you can put U2 in the middle of the domain too. So for this example, I'm putting it slightly on the left, towards the left of the domain, just to show you, kind of the difference in between if you do kind of a smaller element and a larger element. But typically, yes. So typically, you place your nodes such that your elements are kind of equally spaced, just because that's the simplest thing to do. But I'm going to show you basically a case where you don't have to do that. But you can definitely do that. But for like the homework problems and everything, if you want to get the same answers as I do, you should discretize it in the same way that I do. Yeah.
Does a fixed support just like has anything to do with just choosing like a node close to it? I mean, you want like there's something like about a fixed support?
So in reality, actually, yes. So in reality, next to any kind of fixed support, what tends to happen is that the gradients near the fixed support tend to be pretty high. And so like if you imagine like just a simple beam that we're going to load just like this, and so the stresses are actually going to be highest right next to the fixed support, because that's when you go from something that's 0 to some displacement that's right there. So there is a lot of motivation actually in reality to have a finer mesh next to your fixed supports, because that's where kind of the most interesting stresses are going to occur. Yeah. That wasn't the motivation for this problem, but it just kind of happened to be like that. But in reality, that's one consideration for sure. Yeah. All right. So the next question is, the number of nodes are given in the problems we were doing. Yeah. So I'm going to give you basically the number of nodes, at least for these problems. Yeah. So I'll tell you how many nodes, how many elements, and how to space them out. Yep. And so another question is, for this example, 2 total elements is just arbitrary, and we can break it down to more elements. Yes. Yeah. So the choice for 2 elements for this problem was arbitrary. It was more motivated by the fact that I didn't want to spend the whole lecture just writing out a bunch of matrices, so I'm only doing 2 elements. But in reality, yes, you can break it up into more elements, and it's going to lead to a bigger global system. And in that case, it's going to take a little bit longer to form and to solve the problem, but you're going to get a more accurate solution. Yeah, great questions, guys. These are really good. All right, any more questions before we start working this out? Okay. Okay, so let's start forming the element stiffness matrix for element A. Okay. Okay. And so let's write out our formula first. So for element A, so we'll call this Ka. Okay. The way we form the element stiffness matrix is we're going to do integral from x1 to x2. Okay. And so x1 and x2 are going to be the coordinates of the element A. Okay. Then we have our shape function derivatives. So we have d1, dn1 dx, dn2 dx. Okay. Okay. Then we have e times a. Okay. I should have written this on a different line. Okay. Then we have our shape function derivatives again. Okay. And then dx. Okay. And so we basically have a column vector multiplied by e times a, multiplied by a row vector, then times dx. Okay. And so since we're using linear shape functions, we can simply write out the expressions for dn1 dx and dn2 dx. Okay. Okay. Oh, and let's also note that for element A, x1 is going to be equal to 0, and x2 is going to be equal to 5, right? Because element A was kind of our short one, so it goes from x equal to 0 to x equal to 5. Okay. Okay, so for linear shape functions, we know that dn1 dx is equal to 1 over x1 minus x2. Okay, and so if we plug in, x2 and x1 over there, we're going to get minus 1 over 5. Okay, all right, and then we take the derivative of the second shape function, and this is going to be 1 over x2 minus x1, and so this is going to be equal to 1 over 5. Okay, and so we can take these two guys and plug them into our expression right here. Okay, and then we can start to form our matrix. Okay. And so besides that, we also know E. And so E, I think, was 500 pascals, if I'm not mistaken. 5,000 pascals. Okay. Okay. And then for our A, we had our function for that, right? So for A was 1 plus x squared over 400. Okay. So let's go ahead and plug all these guys in. And so first, okay, yeah, let's plug all of these in first. And so after plugging these in, we get Ka is equal to integral from 0 to 5. And then we have our column vector here. So we have minus 1 over 5, 1 over 5, okay, times E, which is 5,000, okay, times our A, which is 1 plus x squared over 400, okay, times our row vector of minus 1/5 and 1/5, okay, dx. And so a lot of these quantities here are actually constants, so we can pull them out of the integral. So this is going to be a constant, this is a constant, and these guys are constants. Okay. And so first thing to do, let's multiply these two vectors together. Okay, so we have minus 1/5, 1/5, and then minus 1/5, 1/5. Okay. And so since this is a 2 by 1 matrix, and this is a 1 by 2 matrix, okay, when we multiply these together, we're going to end up with a 2 by 2, okay, which is going to be our element stiffness matrix. So to get the 2 by 2, first we're going to multiply this 1 minus 1/5 by this minus 1/5, okay, and so that's going to give us 1 over 25. Okay. Next, we're going to multiply the top element by the right element, so this can be a minus 1 over 25. Next, we're going to do the bottom multiplied by the left, and so that's minus 1 over 25. And then 1/5 times 1/5 is going to be 1 over 25. Okay. And then to this, we can multiply 5,000, and then that's going to bring out the outside of the integral. Okay. All right. Any questions on this? Okay. Okay. So if we simplify that, then we're left with the following, and so we're left with 200 minus 200 minus 200 and 200. Okay. And then integral from 0 to 5 of 1 plus x squared over 400. Okay. And so if we perform this integration, what we get is, let's see, 200 minus 200 minus 200, 200. Okay. And then we have x plus x cubed over 1200. Okay. Evaluate from 0 to 5. Okay. And so we evaluate that out, and we're left with the element stiffness matrix for element A, which is simply going to be 1020.83 minus 1020.83 minus 1020.83 and 1020.83. Okay. And so we're left with a familiar site. And so we have a 2x2 matrix here, but we went about it by computing an integral. Okay. Okay, so that's the element stiffness matrix for element A. Okay. And so now let's find the element forcing vector. Okay. So remember, that's a new thing that we have to do here. Okay. And so the element forcing vector, you can kind of think of it as a contribution to the global forcing vector from this particular element. Okay. All right, so the question is, why is there a matrix out of the integral? So basically what we have here is that matrix comes from this matrix on the outside here for this 200, minus 200, minus 200, 200. Okay. And then once we evaluate this integral, you can kind of think of it almost as like a constant that we're multiplying out in front. So it's here, after we perform the integral, we have x plus x cubed over 1200, and we evaluate this from 0 to 5. And so once we plug in 5 into this guy, we're going to get some factor. So we have 5 plus 5 cubed over 1200. And then that constant factor is going to multiply into every element of this matrix right here. Yeah. And so that's how we get this 2x2. So the integral basically just ends up being a scale factor for our matrix that we had already computed from before. Yeah.
So basically just like in the first line, there are two. Okay, the integral is solved, and then on the right side is just the answer to the integral, right?
Exactly. Yeah, yeah. So this
I thought it's like a one thing. Okay.
Oh, yeah.
Got
yeah.
it now. Yeah. Okay.
This is the next step. Yep.
Yeah. Yeah. Get it. Thanks.
Yep. Okay. And so let's evaluate the element forcing vector for element A. So for element A, it's on the left-hand side, so it's on the fixed support. So we don't have a Neumann boundary condition to worry about. And so the only contribution to the element forcing vector is going to be from the body force. Okay. Because remember, we only include the Neumann BC for the elements that actually border that boundary. So in this particular problem, since the Neumann boundary condition is on the right, we're not going to include its contribution here yet, but we are going to do it for element B. Okay. And so the element forcing vector for element A is going to be the following. So we're going to integrate from 0 to 5 of n1 of x and 2 of x, okay, and then multiplied by b of x dx. Okay. And so in this problem, our b of x is just going to be simply 2. Okay, so it's just going to be a constant, and then we can plug into for our element stiffness for our shape functions here, where n1, remember, is going to be x minus x2 all over x1 minus x2, and n2 is going to be x1 minus x over x1 minus x2. Okay, and so same thing we did before. So we're basically going to plug in for these expressions, perform the integral, and then we get our 2 by 1 vector at the end. Okay. All right. Any questions on this? Okay. All right, so let's go ahead and do that. So if we plug in everything, then we end up with an integral that looks like the following. Okay. And so we're going to have 1 over x1 minus x2 okay, multiplied by 2 times the integral from 0 to 5 of x minus x2 and x1 minus x, okay, dx. Right. And remember, so that x1 is equal to 0, x2 is equal to 5, okay? And so we plug everything in and we integrate. Okay. And then we're left with the following. So we have minus 2 over 5, okay? And so that's what you get for from evaluating the terms out in front right here. Okay. And on the interior, we're going to have x squared over 2 minus 5 x. Okay. And on the bottom, we're going to have just minus x squared over 2. Okay. And it's going to be evaluated from 0 to 5. Right. And so once we plug in all the numbers, what we're left with is 5, 5. Okay. And so now that we have the element stiffness matrix and the element forcing vector, we can put them together to form the element system. Okay? And so the element system basically is comprised of the element stiffness matrix multiplied by a vector of the nodal solutions, and then that equals to the element forcing vector. Okay? And so for this element, we have the following. Okay? Okay, so we have 1020.83 minus 1020.83 minus 1020.83, 1020.83. Okay. Element A is going to be acting on nodes 1 and 2, so that's going to be U1, U2. Okay. And then our element forcing vector, which we just found out, is going to be given by 5, 5. Okay. All right. Any questions on how we found this first element system? All right. All right, so that's the system for element A. And so now let's basically just follow the same procedure for element B. Okay. Okay. And so for element B, we're just going to follow the same recipe. So first thing is going to be our element stiffness matrix. Okay. And so KB is going to be equal to integral. In this case, it's going to be x2 to x3 because those are the bounding nodes for this one. Okay. And so we know the coordinates for x1 is going to be 5. So we knew that from the previous one. Okay. And then the coordinate for the upper bound is going to be 20 because that's the x coordinate for the end. Okay. Okay. And so just like before, we're going to have dn1 dx, dn2 dx. Okay. We have multiplied by EA dn1 dx, dn2 dx, okay, dx. Okay. And so again, for this problem, our x1, or our bottom bound here, is going to be 5, and x2 is going to be 20. Okay. And then if we evaluate our shape function derivatives here, we have dn1 dx is equal to minus 1 over 15. Okay. And dn2 dx is going to be 1 over 15. Okay. Okay. And our E in this case is going to be the same, so our E is still going to be 5,000 pascals. Okay. And then our A is going to be given by that function from before. Okay. And so we plug all this in, and we're left with the following. And so we're left with 200 over 9 minus 200 over 9 minus 200 over 9, 200 over 9. Okay. And then integral from 5 to 20 of 1 plus x squared over 400, okay, dx. Right. And so you evaluate this integral, and then what you're left with is 479.17 minus 479.17 minus 479.17, 479.17. Okay. All right, question. Okay. And so the question is, how is this different from what we have done before with the bar and the truss problem with 1D? Is it the freedom that we now have with discretizing? So that's part of it. And so part of it is you have greater freedom with the discretizing. And the second part of it is that you can actually do this for any kind of differential equation. And so we're basically working through these examples for kind of the basic differential equation, which is just a second order differential equation. But you can actually apply this method to any differential equation that you can think of. Right? So it's a much more general framework. And one other thing that's going to be different specifically for this problem is our area. Okay. And so we actually have a varying area in this case. So our area is actually going to get larger, as we move along the bar, right? And so our function for the area is given by this 1 plus x squared over 400. And so we didn't have this freedom before. So before, when we had a bar element, it was kind of fixed with just one area because it was just, a bar that had constant cross section. But with this framework, you can basically have situations like this, where we have a bar that's growing, and you can have the opposite where the bar is tapering off and the area is getting smaller. Or even more interesting, you can even have a case where the Young's modulus is going to be changing throughout the bar as well. And so you might have cases where, you have like a composite material where the Young's modulus changes from, one side of the bar to the other. Okay? And with this framework, you'll be able to kind of very easily kind of account for that. Whereas if you're kind of doing it with the older method, you're going to have to do some assumptions and some kind of finagling. So, so this method of performing finite elements with the shape functions and everything, it's a lot more general, and it can handle basically any boundary value problem that you can throw at it. Okay. Yeah. All right. So the question is with anisotropic too. So anisotropic basically is a word to describe how material properties can change within a material. So not only the value of the material property, but also kind of the direction of it. And so in this case, we're assuming that the Young's modulus is isotropic. And so basically, it's what that means is that we have basically a constant Young's modulus that's the same in every direction. But this can handle those cases too. But you kind of have to use a slightly different formulation. So for 1D problems, you don't see any anisotropy because we're just going in one direction. But once we get to 2D and 3D problems, that's when we can start to introduce, the Young's modulus is stronger going this way versus this way. And you can actually account for that in the formulation as well. So, this way of doing finite elements off the boundary value problem, it's really versatile. So it's, you can basically solve anything with it. Yep. Mm-hmm. All right, any more questions on this? Once you guys type that out, I'm gonna turn on the light because my eyes are kind of straining a little bit. Okay. I need one of those like gamer goggles, but to prevent eye straining, so I can like play in the dark. But yeah, those things are getting really expensive now. Okay, so that's our element stiffness matrix. Okay, and so now let's do our element forcing vector for the for element B. Okay. And so our element forcing vector is going to be the same as before. So we have our contribution from the body force. Okay. Okay. And so our contribution from the body force can look like this. So integral from 5 to 20 of n1 and 2 b of x dx. And so I'm going to skip the steps here because, I want to make sure I get to Gauss quadrature. But basically, you would apply this this integral in the same way. And so from this, we get basically 15, 15. Okay. Okay. And so that's one boundary condition, or that's one contribution to the forcing factor. Okay. But for this particular element, since this element borders the Neumann boundary, we have to add an additional contribution. Okay. And the contribution is going to look like this. Okay. So when x is equal to x3, and so basically when we're on the right side of this element, which is the very edge of our domain, we have to add the following to FB. Okay. Right. So what we're going to add is basically our shape functions here. So we have N1, N2, okay, multiplied by A, which is the area at X3, okay, and then times our tension. Okay. And so our area at X3, we're basically just going to plug in our area function and apply it at X3. And so this is going to be 1 plus X3 squared over 400. Okay. And so since X3 is equal to 20, this is just going to be equal to 2. Okay. And then we know our T bar right here is going to be minus 5 from the problem. Okay. Okay. All right. And so that's not the only thing. And so we have to evaluate these guys at the boundaries too. Okay. And so we're going to evaluate N1 at X3, right? And so the function for this is going to be, let's see, X3 minus X3 all over X2 minus X3. Okay. And so this is actually going to be 0. And so N2 at X3 is going to be, let's see, oops, X2 minus X3 all over X2 minus X3. Okay. And so this is going to be 1. Okay. And so the contribution to the element forcing vector from the Neumann boundary condition is going to be 0 and 1. And so that's what you get for evaluating the shape functions at the boundary. Okay. And then we're going to multiply it by 2, which is from the area. Okay. And then we're going to multiply it by minus 5, which comes from the boundary condition itself. Okay. And so we have an element forcing vector contribution of 0, minus 10, right? And so the total element forcing vector from element B is simply just going to be the sum of these two guys. Okay. And so if we take 15, 15, and we add that together to 0 and minus 10, what we get is 15 and 5. Okay. Okay. And so remember, you know, if your element borders the Neumann boundary condition, you have to account for that into your element forcing vector. Okay? So you actually have to evaluate both the forcing vector due to the body force and also the forcing vector due to the Neumann boundary condition. Okay. And remember, you know, when you're evaluating this entire expression right here, like the N1, N2, A, T bar, you know, you evaluate it at the x coordinate of your Neumann boundary. All right, any questions on how we obtain this element forcing vector? Okay. Okay, and so we put it all together, we can form our element system for element 2, or element B, sorry. And so for element B, we have a matrix of 497, or 479, sorry. 479.17 minus 479.17 minus 479.17 and 479.17. Okay. The nodes that it's acting on are nodes 2 and 3. Okay. And this is going to be equal to 15 and 5. Okay. All right, so now that we have the element systems for both element A and element B, the next step is going to be to assemble. Okay. Okay, so we've done this before, so it's so assembly is not anything new, and so the only thing that we have to worry about now is we have to include, you know, the element forcing contributions. Okay. And so in this case, since it's a 1D case, you know, we don't have a lot of mixing around. And so I'm going to highlight in red right here where you would put the system for, you know, element A. Okay. Okay. And so the element system for element A, which includes the matrix and the forcing vectors, you would put in there. Okay. And then in purple right here, I'm going to indicate the locations where you put the element forcing vector and element stiffness matrix for element B. Okay. All right. And so I think if you do that, what you end up with is something that looks like this. Okay. And so we have, I'm not gonna be able to fit it, but 1020.83 minus 1020.83 minus 1020.83. And then in the middle right here, we have 1500. And then minus 479.17 minus 479.17, 479.17. Okay. And on the right here, we're going to have 5, 20, and 5. Okay. And then in all the other areas, we have 0. Right. But we're not done yet, so we still have to include our Dirichlet boundary conditions. Okay. And so in this case, our Dirichlet boundary condition is on node 1, right? And so since that tells us that U1 is equal to 0, and so we're going to use the exact same row replacement method that we did before. And so if U1 is equal to 0, I'm just going to replace this entire first row, okay, with 1, 0, 0, and then 0, okay? Right? And so once you have the global system like this with the boundary conditions, you can go ahead and solve, okay? And so solving the system, you should get the following. So you get U1 is equal to 0, U2 is equal to 0.0245, and U3 is equal to 0.0349. Okay. Right. So everything that we just did just now is, you know, we've all done that. We've done that part so many times now. So it's just assembly, boundary conditions, and then solve in MATLAB or by hand if you're into that kind of thing. Okay. All right. So that's basically how you take a boundary value problem and turn it into a finite element problem. So you know the process in which we went through to get the element stiffness matrix, and in this case the element forcing vector is going to be different. But from there, you know, you can just basically follow the same process in which we did before. So you just assemble it all into one system. You apply the boundary conditions and you solve. So hopefully there's a mix of, you know, things that look familiar and new stuff too. Okay. Any questions on this before we move on? Okay. And so before I move on to kind of the next topic, you know, I just want to kind of make note of a couple of things. So I think you guys kind of have noticed a lot of these already, but I think it's kind of worth repeating in this case because, you know, we're going to be doing a lot of integrals and stuff like that. Okay. And so what you should notice from an element stiffness matrix like this, you know, you'll notice the matrix is symmetric, right? And this was this was true for our frame and beam and truss problems too, right? So all of our element stiffness matrices were symmetric. And so if you're solving for your element stiffness matrices and they're not symmetric, then something probably went wrong in your calculation. So it's always good to check. Okay. The other thing is, you know, just because we're solving these just because we're getting these matrices in a different way, don't forget to apply your boundary conditions. So it's a little bit easier to miss them in this case because, you know, we're going to be doing a lot more math than usual. But don't miss your Neumann boundary conditions and don't miss your Dirichlet boundary conditions too. So definitely make sure you have those accounted for before you actually hit solve and try to solve it in MATLAB. Okay. Okay. So that's the basics of the process. And so with that, you know, you should be able to do your homework just fine. But I do want to cover, you know, one more topic, which for 1D, it's not going to make that big a difference. Although, you know, on Monday, what I plan to do is, you know, to implement one of these MATLAB. And so we'll actually use this in that MATLAB code, but we won't actually see the power of this technique until we get to 2D finite elements later. Okay? And it's this idea of numerical integration. But so the specific name for this technique is going to be called Gauss quadrature. Okay. Okay. And so what you should notice from the last example is that we've had to do a ton of integrals, right? And integrations can get really annoying, right? Especially for really complex functions, performing tons and tons of integrals can really become a pain. Okay. And actually, once you start doing these problems, you'll start to realize that the integration is kind of the bottleneck. So you spend most of your time doing your integrals more than you do kind of anything else. And so it'd be really nice if there was a way to evaluate these integrals in a simpler way, especially once we start evaluating these in code. So once you're in code, having an easier way to do integrals is actually kind of a godsend. Okay? And so, the way that we're actually going to do this is to actually not do the integration, is to not actually perform any integration. Or in other words, we're not going to actually perform any antiderivatives. And so what we're going to do instead is we're going to approximate integrals, okay? And the way that we're going to approximate them is that we're going to just do it through a weighted sum. Okay. And so the idea looks like this, basically. Okay. And so let's say that we have an integral that we want to evaluate. Okay. And so for the integration bounds, I'm switching to a new variable called zeta, which I like to call just tornado, because the way I draw that looks like tornadoes. Okay. Let me do this. Let me do this actually. So instead of just to make these different, I'm going to make these integration bounds zeta A and zeta B. Okay. Okay. So I want to make sure that these bounds are different from the zetas that I actually plug into these. Okay. And so I have a dot 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 here because this can actually continue on forever. Okay. Okay. And so a few things you should notice here. So instead of actually performing an integral, what you should see is that what we have on the left and the right here is that this function f is the same, okay? And so f here is our integrand, okay? Right? And so to evaluate this, so normally when you evaluate the integral, you take the integrand and you take the antiderivative of it, and then you apply it at the bounds, okay? But actually, the most time-consuming part of performing an integral is actually performing that antiderivative of the integrand, okay? And so the idea with Gauss quadrature is to say that, we're not going to bother finding the antiderivative of the integrand. What we're going to do instead is we're actually just going to evaluate the integrand at some key locations, okay? Okay? And then sum them together. Okay? But then when we sum them together, we're going to multiply each term by a weight. Okay? Okay? And so that's what these W1s and W2s are. So these are the weights that we're going to apply to the sum. Okay? Okay. And so with this method right here, basically you get out of doing the antiderivative altogether. Okay. And so this is actually really clutch for cases where finding that antiderivative can be really tough, right? Especially for code. So it's very easy to tell a code to evaluate this function. It's very difficult to teach a code to do an antiderivative. Okay? And I know that there's stuff out there right now like Wolfram Alpha and stuff like that that can do it. But MATLAB is not nearly as smart as Wolfram Alpha. So if you tell it to find the antiderivative of something, it's just going to give you an error, or it's just not going to do it. And so forming the integration in this way is actually a lot more easy. It's a lot easier to implement in code than it is to actually find the antiderivative. Okay. And so just to kind of connect this to something that hopefully you've seen before, this idea of evaluating integrals through a sum. Hopefully you've seen this before in a previous math class. So this is similar to a Riemann sum. Okay? It's not quite the same, so there's going to be differences, but the idea is the same. Where instead of performing an antiderivative, we're just going to sum up a bunch of stuff. Okay? All right. So the question is: a more curvature and critical geometric features equal more weighted points? That's a great question, actually. So the number of weighted points that actually are chosen actually depends a lot more on the order of the function that you're putting in. And so if you have like a quadratic function versus like a cubic function versus a linear function, that's actually the bigger driving factor to how many points that you should include for your weighted sum. Yeah. Yep. All right, any questions on this? Okay, so that's actually a great segue, because the choice of how many points that you want in your sum is a choice. Okay, there's better choices than other ones, but you can actually choose it. Okay, and the idea behind the number of points is that the more points that you include, the more accurate it's going to be, but also the more cost it's going to have. So I have this table here that's kind of nice. Okay. And so in this first column right here, I'm going to call it a number of GP. And so GP stands for Gauss points. Okay. So I'll go up to 3. Okay. And so in addition to the Gauss points, we have to tell where those Gauss points are. So these are going to be the locations. Okay. And then we also have the weights that are associated with this. Okay. Okay. And so if we only have one Gauss point, it's actually pretty simple. And so the Gauss point, the location for that is going to be zeta is equal to 0. Okay. Oh, and let me state that these locations here assume that zeta A is equal to -1 and zeta B is equal to 1. Okay. And so the integration bound, these are only for when the integration bounds are net -1 to 1. Okay. And the weights for this are going to be 2. Okay. And so if you have 2 Gauss points, then the location is going to be -1/√3 and then 1/√3. Okay. And those cases, the weights are going to be just 1 and 1. Okay. And then for 3 Gauss points, it looks something like this. Okay. All right, so we're going to have 1 Gauss point at -√3/5. Our second one's going to be at 0, and our third one's going to be at √3/5. Okay. Okay. And our weights are going to be 5/9, 8/9, and 5/9. Okay. Okay. And so these are the Gauss points and the locations and the weights for all these different ones. Okay. And so I'll tell you right now that the ones that are most often used in practice are going to be 1 Gauss point. Okay. And so the nice thing about 1 Gauss point is this works perfectly for a linear function. or when your integrand is a linear function. Okay. Which, if you have a linear shape function, happens more often than not, right? And the next one often that's used is 2 Gauss points, and this works perfect for quadratic integrands. Okay. And so that's kind of the next most common case in finite elements, where if you use a quadratic shape function. Okay. Okay, and so let's do an example to basically see this in action on the next page. Okay. Before we do that, are there any questions on this?
I actually have. So how do you determine these numbers? Like you just solve the integral numerically and then get these? I don't know. I don't get it.
Right. So to get these numbers, I'm skipping the proof of these. So there's a proof that you can do to basically show that these locations and these weights are kind of the most optimal for the Gauss quadrature points. But I'm skipping that for this class just because it's a pretty lengthy proof. But it's pretty well known. So I think it's even on Wikipedia. So actually, if you search up a Gauss quadrature, I think it'll show you the same table with these points. It'll run through the proof for you too. So yeah, that's a great question, because these points weren't just pulled out of a hat. These are kind of the most mathematically optimal points to perform your integration as best you can. But it's pretty lengthy and kind of a little bit outside the scope of finite elements. So if you're interested, I would definitely look it up. But yeah, I'm going to skip over it for this class.
Got it. Thank you.
Mm-hmm. Okay, so let's do an example. Okay, and so let's evaluate the integral. Integral from 0 to 1, or minus 1 to 1, of 3x squared minus 2. Okay. And so let's evaluate this using a 2-point Gauss quadrature. Okay. Okay. And so just to show you that this Gauss quadrature stuff is actually real and it's not made up, I'm going to evaluate this integral exactly first. Okay. And so this exact integral, we're just going to take the antiderivative of this. So then we have x cubed minus 2x, okay, evaluated from minus 1 to 1, right? And so if we plug in minus 1 and 1, then we get minus 2 from this. Okay? And so our Gauss quadrature should get us minus 2. Okay? Because first of all, we have a quadratic function here. So we have 3x squared minus 2. And if we use 2 Gauss points, it should be able to recreate this integral exactly. Okay. Okay. And so when we evaluate this 2-point rule, let's evaluate our f. Okay. And so our f in this case is going to be 3x squared minus 2. Okay. So that's just simply your integrand. And so what we're going to do is we're going to sum up 2 different Gauss points of our integrand. Okay. And so the first one, so we're going to do basically W1 f of zeta 1 plus W2 f of zeta 2. Okay. Where zeta 1 from the previous table is going to be minus 1 over root 3, and zeta 2 is going to be 1 over root 3. Okay. Oops. And then W1 is going to be equal to 1, and W2 is also going to be equal to 1. Okay. And so if we evaluate this, we have 1 times f at minus 1 over root 3. So this can be 3 minus 1 over root 3 squared plus minus 2. Okay. Plus 1 multiplied by 3, 1 over root 3 squared, minus 2. Okay. And so we evaluate this. Then we have 1 multiplied by 1 over root 3 squared, just 1 over 3. And so we have 3 over 3, which is 1 minus 2. Okay. Plus 1 times 1 minus 2. Okay. Because 1 over root 3 squared is 1 over 3 minus 2. And we get minus 2. Okay. And so it's as simple as that. So you basically just have to evaluate the integrand at the locations, multiply by the weights, and then just add them up. So there's no antiderivatives to take place. Okay? And so for polynomials, I know this is pretty trivial because you can argue that for this problem, it was just way easier just to perform the integral anyway. But for more complicated functions, and more importantly, for when we get to 2D, and we won't get into it, but you can imagine in 3D too, this Gauss quadrature is a godsend because it really simplifies the work, especially the ones that you're going to do in code. Okay, any questions on this? Okay. And so, the question that you might be asking for at this point is, you can say, wait a second, the requirement in order for us to use Gauss quadrature is that our integration bounds have to be -1 to 1. And so that's extremely restricting, right? So if you go back to kind of the first example that we did today, we had integration bounds that were not -1 to 1, right? And so if we can only use Gauss quadrature when it's -1 to 1, that kind of seems pretty useless actually, because a lot of the integrations that we're going to perform are not that. Okay? But you can actually apply Gauss quadrature in these cases, but you have to perform a change of variables. Okay. Okay. And so let's look at just kind of an arbitrary function, an arbitrary integral. Okay. So we have integral of x1 to x2, okay, of f of x dx, okay, where x1 and x2 can be anything in this case. Okay. And so in order to put this into Gauss quadrature form, we have to have an integral from -1 to 1. Okay, so that's non-negotiable. Otherwise, we can't use the table. But we have to perform a change of variable. So what that means is that we're going to have an f of x, but we're going to express x in terms of our zeta coordinate. Okay. And so what this means is that we're basically going to change from an x coordinate to a zeta. Okay. And in addition to that, we're going to multiply by this extra guy right here. Okay. Where this extra guy is called the Jacobian. And so the Jacobian, you can kind of think of it as a scale factor that allows you to perform a change of coordinates. Because we're performing kind of a drastic change here. So we're changing from, any arbitrary integration bound from x1 to x2 to an integration bound that goes from -1 to 1. Okay. Okay. And so in order to actually perform this conversion, we need two things. Okay. And so first of all, we need x of zeta. And so what this is the physical coordinate, x, as a function of the Gauss coordinate. Okay. Okay. And the next thing that we need is this our Jacobian. Okay, so we need dx d zeta, and this is our Jacobian. Okay. And luckily, these two are very closely linked. So once we find one, we can find the other one pretty easily. Okay. All right. Any questions on this? Okay. And so let's establish x of zeta first. And so for x of zeta, basically we need to find a relationship between the physical coordinate and the Gauss coordinate. Okay. And so I'm going to do something that that kind of brings this kind of back to what we've been doing. Is I'm going to use the same shape functions. Okay. In this case, the same linear shape functions. Okay. So remember, this is n1 and n2. Right. To relate these two quantities. Okay. Because remember what we use n1 and n2 for, right? And so with at first, so this is a flashback, so I'm going to put this in parentheses here. Okay. And so the first thing we use n1 and n2 for is to interpolate our nodal solution values to any point within the element. Okay. And so we had ue of x is equal to u1 n1 of x plus u2 n2 of x, right? And so what that basically allowed us to do was to take our nodal solution values u1 and u2 and then interpolate them anywhere else. Okay. What if we use the same shape functions to express the nodal coordinates? And so we can say that x of zeta, okay, is equal to x1, and so x1 is the coordinate for our first node here. Okay. Okay. And we're going to multiply that, by n1 of zeta. Okay. So we're going to have the same functional form for it. And then to that, we're going to add x2 times n2 of zeta. Okay. And so it's the same idea, but instead of interpolating the nodal solutions, we're going to be interpolating the nodal coordinates. Okay. Okay. And so our shape functions here are going to take the same form. Okay. And so our n1 is going to be zeta minus zeta 2 over zeta 1 minus zeta 2. Okay. And then our n2 is going to be zeta 1 minus zeta, and then over zeta 1 minus zeta 2. Okay. But for this particular case for Gauss quadrature, we can actually simplify this a little more. Okay. Because remember, the reason we're performing these change of variables is because our zeta 1 and zeta 2 have very special values. And so we know the fact that, we're performing this change of variables for Gauss quadrature, that zeta 1 has to be -1 and zeta 2 has to be 1, okay? And so if we plug these guys into these expressions, we get kind of much simpler versions of these shape functions, okay? And so for n1, we have 1/2 times 1 minus zeta, okay? And then n2, we have 1/2 1 plus zeta. And so these are, a little bit easier to deal with because they're much simpler expressions. Okay. All right. Any questions on this? Okay. All right. So one quick thing before we end today is I want to show you how to compute the Jacobian. Right. So the Jacobian is nothing more than just dx d zeta. But because we've formed this relationship between x and zeta using the shape functions, we can use this exact same expression to basically find our Jacobian. Okay, and so dx d zeta is just going to be x1 dn1 d zeta plus x2 dn2 d zeta. Okay. And so if we evaluate those integrals, then we get dn1 d zeta is going to be -1/2, and dn2 d zeta is just going to be 1/2. Okay. And so this is going to be minus x1 over 2 plus x2 over 2. Okay. And so this is just going to be simply x2 minus x1 all over 2. Okay. Okay. And you can simplify this a little bit more because, you know, oftentimes we like to express things in terms of the length of the element. Okay. And so if we define LE to be x2 minus x1, then our Jacobian dx d zeta is simply just going to be LE over 2. Okay. All right. Any final questions on this? Okay. So that's all we got time for today because it's 6:45. And so what we'll do on Monday is I'll do just one quick example to basically show you, you know, how you would do this change of variables. Okay. And then from there, we're gonna have another kind of code walkthrough where I walk you through the implementation of a finite element code like this for 1D problems. Okay. Okay, so thanks everyone for tuning in today. So I have another minute paper that's up on Canvas. So if you want to fill that out, definitely feel free. But besides that, you know, hope everyone has a great weekend. Thanks everyone for tuning in, and I'll see you on Monday. Yep, thanks, Chris.
Excuse me.
Yep, what's up?
So yeah, I have a question. Is this change of variables like from x to zeta? Do we need it for this homework 3?
No, you don't need this for homework 3. So homework 3 you can solve for basically everything that we did right before we started Gauss quadrature. So this Gauss quadrature actually is going to be something that's used a lot more for code than it is for hand calculations, because because we're doing 1D problems here, so a lot of times it's just way easier just to evaluate the integral. But you know, for 2D and 3D problems, it's going to be a lot easier to do this instead. Yeah.
Get it. Thanks.
Yep. Mm-hmm.
Oh, another question, by the way.
Sure. Mm-hmm.
So, you know, like I'm still working on the homework.
Yep.
I had a question about it.
Okay. Yeah, what's up?
So, you remember about the video and the ANSYS activity about the bike crank? You said that we need a fixed support in like one of those holes up there. But I just thought it's like it should be a pin support because it's basically the crank is just rotating. It's just not moving in X and Y direction, but it's basically rotating. So it should be a pin support. That's what I think. Okay.
Yeah, so I think that's true. So, you know, normally the bike crank does rotate like that. But for this particular problem, we were just looking at just the bike crank you know, just right before it reaches that rotating part. So the rotating part actually is kind of a different part of the bike. But you can definitely argue that you can use a pin support for that too. I think the problem is if you use a pin support for the for kind of the hand calculation problems, for the hand calculation part, you wouldn't be able to find a solution because there's nothing there that's going to restrain the rotation. And so you might get like an infinite rotation there.
Okay, so I used that fixed one, but because I was just like thinking, so I thought like, why is it like a fixed support? That's why I just wanted to know why. Okay.
Oh yeah. No, it's I think probably the better answer for that is because we needed to constrain this in a way that we could solve it. And so it's definitely a much simpler version than what a bike crank is in reality. So I think in reality, I think you're right. So it is closer to a pin support, but because we're kind of just looking at a simplified version of it, we kind of have to make it a fixed support, just so that we can solve it. Yeah.
Get it. Thank you.
Yeah.
Have a nice weekend. Bye.
Thanks. You too.
Professor?
Yeah.
Can I ask a quick question?
Sure. What's up?
So when we're doing the element forcing vector, I think it was the example we were doing.
Yep.
When we add the following to the force FB.
Yep.
I'm just wondering, like why do we add that to FB again?
The Neumann boundary
so
condition.
that part.
Yeah. So and so remember the the way that we apply the Neumann boundary conditions for these problems is a little bit different, because remember the Neumann boundary conditions are baked kind of directly into the weak form. And so when we formed the weak form, we had our 3 integral expressions there. Once we added them up and we evaluated it, then we also had this term for the Neumann boundary condition. So it's just for this weak form, because the Neumann boundary condition comes out naturally from the problem, yet we have to add it in this way. So we don't add it in the same way that we did before, where we just simply add the condition over to the end. Because you can see right here, even though we had a Neumann boundary condition of 5, we end up adding a -10 for this one. And that's because you have to interact both the Neumann boundary condition together with, the shape functions and the area in order to get the proper one. Yeah.
Okay. And the reason why you applied it at the third or at position B was because that's where the -5 pascals is occurring?
Yes. Yeah.
That's why you only added at from 2 to 3 or U2 to U3.
Exactly. Yeah.
Okay, so that's why you don't add it from U1 to U2 because
exactly.
Okay,
Right.
okay,
Right.
okay,
Right.
all right. Thank you.
Yep. Mm-hmm.